Imagine this. Every single conversation you have with an AI, every email it drafts for you, every image it conjures, what if each of those digital interactions came with a hidden physical cost? We're not just talking about the electricity bill, but something, well, far more fundamental. Water. Today we're taking a deep dive into the often overlooked environmental footprint of artificial intelligence, specifically its surprisingly significant water consumption.
That's a crucial point, and it's exactly why this topic needs this kind of deep dive. Our mission here isn't to simply label AI as, harmful or good.
Right, it's more nuanced than that.
Definitely. It's about pulling back the curtain on the underlying infrastructure, really understanding the complex trade-offs involved, and exploring the civic choices we face as this technology integrates deeper into our lives.
Okay.
We'll unpack where these effects actually come from, how they can vary so wildly depending on, well, a whole myriad of factors, and critically, what can actually be done to reduce them.
So the goal is for you, the listener, to be better equipped to balance that innovation with sustainability.
Exactly, in this age of AI.
That's a vital distinction. And thankfully, we've got some fascinating, really cutting-edge research and academic insights that help quantify this hidden cost. What were some of the biggest surprises, maybe counterintuitive findings, that emerged when you started looking into the actual footprint?
Well, one of the most surprising things, I think, for many people is just how tangible this digital cost becomes when you look at the water aspect.
Mm-hmm.
It allows us to go beyond just assumptions and truly grasp AI's actual footprint in a way that's both surprising and incredibly informative.
Okay, let's unpack this then. Maybe start with a figure that might just make you do a double take. Did you know that a short conversation with an AI model like GPT-3, from OpenAI's ChatGPT system, or even just drafting a quick 100-word email using it, could consume as much as 500 milliliters of water?
Wow.
Yeah, that's the equivalent of a standard single-serving water bottle. Suddenly, my quick AI chat feels a lot less virtual, maybe a lot more like a trip to the water cooler.
It truly is a striking figure, and it's really important to understand what it actually encompasses. That estimate isn't just about the electricity visibly powering the computers in a server rack.
Right, it's more complex.
It accounts for the substantial amount of water consumed to cool the data center servers where those AI computations happen, and the additional water used often far away at the power plants generating all that electricity in the first place.
Ah, okay.
It's a much more holistic view, almost a full life cycle perspective of that one interaction.
And what immediately struck me about the research was this. It revealed an AI system's water usage isn't some fixed number at all. It can vary wildly,
Hugely.
depending entirely on where and when the computer answering your query is actually running. So context really is everything, isn't it?
Absolutely. To understand that variability, we really need to look at the two primary hidden streams of water use. The first is directly within the data center itself for the on-site cooling of servers. These machines, they generate an enormous amount of heat, and that heat has to go somewhere, right? To prevent failures and maintain efficiency.
So are we talking about those giant cooling towers? Sometimes people call them misters, the ones you see in pictures of data centers. How exactly do they work to get rid of all that heat?
You've got it. Think of them as giant misters spraying water over hot pipes or sometimes open basins. The basic principle is evaporation. As the water evaporates, it carries heat away from the servers, cooling them down.
Simple physics, really.
Exactly. It's an incredibly efficient method for heat removal, thermodynamically speaking. But that evaporated water is, of course, removed permanently from the local water supply, whether that's a river, a reservoir, or an underground aquifer.
Gone into the atmosphere.
Precisely. Now, there are other cooling systems that might use less water, but they often consume significantly more electricity. Which leads us neatly to the second stream of water consumption.
Right. The second stream,
Yeah.
the water used by the power plants themselves. This is often an even bigger hidden factor, isn't it?
It often is, yeah.
We're talking about the truly immense volumes of water that traditional power plants, coal, natural gas, even nuclear use for their steam cycles to generate electricity, and then critically, for cooling their own equipment.
That's it. It's not just the server room you need to think about. It's the entire grid powering it, often far upstream.
So it ripples outwards.
Precisely. And the impact extends beyond just fossil fuels and nuclear. Even hydropower, which might seem inherently green because it doesn't burn fuel,
Right, you think of dams and rivers.
it still consumes water through evaporation from its massive reservoirs. I mean, consider the vast surface areas of these artificial lakes. Sunlight and wind are constantly pulling water from them.
I hadn't really thought about that evaporation aspect of hydropower.
It's often overlooked. Then you have concentrated solar plants, which are a bit different from the photovoltaic solar panels you might see on a roof.
Okay, how so?
These facilities use mirrors, sometimes thousands of them, to focus sunlight onto a central point to heat a fluid. That hot fluid then drives a turbine to generate electricity, much like a traditional steam power station.
Ah, so it's thermal.
Exactly.
Right.
So they can also be quite water intensive if they rely on similar wet cooling methods for that steam cycle.
That's a really crucial distinction because in stark contrast, you've got wind turbines and standard solar panels, PV panels. Once they're built and installed, they use almost no water at all, right?
Pretty much zero for operation, aside from maybe a tiny bit for occasional cleaning.
Yeah. So this immediately highlights that depending on our energy mix, the way we choose to power these AI systems, there are fundamentally different paths we can take, paths with vastly different water implications.
Absolutely. And that where and when we mentioned earlier, it profoundly impacts both of these water streams.
How so?
Well, consider, for example, a data center located somewhere cool and humid, like Ireland. Such a facility can often rely heavily on just using the outside air for cooling, or maybe specialized chillers that don't use much water. It might run for months with minimal water use for cooling, just leveraging the naturally cool environment. It's almost an ideal climate for water-efficient operations.
But then, flip side, imagine trying to run that exact same data center in, say, Arizona in July. The difference must be just staggering.
It is indeed. In that kind of environment, scorching temperatures, extremely dry air, a data center would be heavily dependent on evaporative cooling.
Because it works better in dry heat.
Exactly. Hot, dry air makes that method incredibly effective for removing heat rapidly. But, as we discussed, it also consumes massive volumes of water because that evaporation process is working overtime, constantly needing replenishment.
Right. And it's not just the geography. Timing plays a huge role, too. You mentioned a study.
Yeah, a study from the University of Massachusetts Amherst really highlighted this. They found that a data center might use only half as much water in winter as it does in summer.
Half. That's huge.
It is. Think about a midday heat wave. Cooling systems are absolutely maxed out, working in overdrive to keep everything stable. But demand is significantly lower at night or in cooler months. So when those AI computations actually happen, truly matters for their environmental footprint.
Okay, so location, time of day, season. But are there technological solutions, things being developed?
Definitely. This brings us to some promising alternatives that are being actively explored and developed, aiming to mitigate this water impact. One really innovative approach is called immersion cooling.
Immersion, like dunking the servers.
Basically, yes. Servers are actually submerged in specialized non-conductive fluids, things like synthetic oils. This method can reduce water evaporation almost entirely because the heat is transferred directly to this liquid, which is then cooled in a closed-loop system.
Wow, that sounds like a potential game changer. And I've also heard about Microsoft pushing a zero-water design concept. What exactly does that entail? Does it mean literally no water use at all for cooling?
Well, for the core cooling process, yes, it's a huge leap. Microsoft's design aims for zero water for cooling by circulating a special refrigerant-like liquid through sealed pipes directly across the computer chips.
Okay, like direct contact cooling.
Exactly. The liquid absorbs the heat and then releases it through a heat exchanger in a closed-loop system, entirely eliminating the need for evaporation for that main cooling function. But, and this is an important clarification, it's zero water for cooling.
Ah, okay.
The data centers would still need some potable water for, restrooms, maybe kitchens, other staff facilities, so it's not entirely water-free overall. Still, it dramatically reduces the environmental impact of the core cooling, which is the big water user.
That's an important caveat, but still incredibly impressive. I imagine, though, such cutting-edge solutions probably aren't quite mainstream yet. What are the hurdles stopping wider adoption?
That's right. They're not yet widespread. It really boils down to several factors. There's the higher initial cost of implementing these new systems.
Always a factor.
Always. Then there's the added complexity of maintenance compared to traditional, well-understood methods. And honestly, The significant challenge and cost of converting existing data centers, retrofitting them to these entirely new cooling
Yeah,
paradigms.
you can't just rip out the old plumbing easily.
Not when you're dealing with that scale and complexity. So for now, most operators still largely rely on those traditional evaporative cooling systems because they are proven, relatively cost effective, and, well, people know how to run them.
Okay, so we've talked location, timing, cooling tech.
Hmm.
But what about the AI itself? Does the type of AI matter?
Oh, absolutely. Beyond the physical location and the cooling methods, the actual type of AI model you query matters significantly.
How so?
It's because different models have wildly varying levels of complexity. They require different hardware, different underlying architectures, and ultimately different amounts of processor power to run.
Makes sense.
Some models, just because of their intricate design or sheer size, can consume over 70 times more energy and consequently more water than ultra-efficient ones that have been highly optimized for performance and resource use.
70 times. That's a huge difference. And this actually leads us to something really empowering for you, our listener.
Yeah.
A simple skill you can use to maybe get a rough estimate of AI's water footprint yourself. You don't need a supercomputer or a degree in thermodynamics.
Exactly. It's basically a three-step process, and you really don't need advanced math to follow along. Step one, you need to find the energy consumption per prompt. This is typically measured in watt hours, which is essentially how much electrical power is used over a period of time for that single query.
Okay, watt hours per prompt. Where do we find that?
Well, it's getting better, but it often comes from independent analyses or sometimes company disclosures. For example, some analyses estimate that a medium-length GPT-5 response, maybe 150 to 200 words, uses about 19.3 watt-hours.
19.3 W for GPT-5. Okay.
Yeah. Whereas a response of similar length from a more optimized, newer model like GPT-4o uses significantly less, around 1.75 watt-hours.
Wow, quite a drop. 1.75 AJ for GPT-4o.
And Google, in their public reports for their Gemini system, claims a median text prompt consumes just 0.24 watt-hours. Though it's fair to say they don't specify the exact length of complexity, so a direct comparison to those GPT figures isn't quite apples to apples.
Got it. 0.24 AJ for Gemini Media. Okay, so we have the energy in watt hours. What's step two?
Step two is to use a practical estimate for the amount of water consumed per unit of electricity. We call this the water factor, and it's usually measured in milliliters per watt hour,
And
MLWH.
milliliters per watt hour. Okay.
And this factor tries to combine both the on-site cooling water within the data center and that upstream water use at the power generation facilities. Based on independent research and some industry reports, a reasonable range to use today is about 1.3 milliliters per watt hour for highly efficient facilities.
1.3 for efficient.
Up to maybe 2.0 milliliters per watt hour for more typical average sites.
2.0 for typical. Okay, and for step three, I assume we just combine these numbers.
That's right. Step three is where you put it all together with simple multiplication. The formula is pretty straightforward. Energy per prompt, NWH, multiplied by your chosen water factor, in MLWH, equals the total water consumed per prompt, in ML.
Right, let's run some numbers then, make this concrete. For that medium GPT-5 query, we mentioned 19.3 Warwick. Let's use the typical efficiency estimate of 2 milliliters per watt hour. So 19.3 times 2.
Gives you about 39 milliliters of water per response.
39 milliliters. Okay, that's nearly a quarter of a cup, which, yeah, it certainly makes you think. But now for that medium GPT-4o query, 1.75 water using the same 2 millWH factor.
It's 1.75 times 2, which brings us way down to just 3.5 milliliters.
Just 3.5 milliliters. That's a huge difference already.
It is. And now, if we consider those more efficient facilities using the lower 1.3 millWH water factor,
Okay, the 1.3 factor.
then those numbers drop even further. GPT-5 goes down to about 25 milliliters, 19.3 by 1.3, and GPT-4o drops to roughly 2.3 milliliters, 1.75 by 1.3.
25 milliliters and 2.3 milliliters. And what about the Google Gemini figure? They reported 0.24 watt hours and claimed about 0.26 milliliters per medium prompt.
Exactly, which is incredibly low, roughly the volume of just 5 drops of water.
Wow. The difference between, say, 39 milliliters and 0.26 milliliters is just incredible.
Right, and what becomes crystal clear from these calculations is that the huge range in these estimates from less than half a milliliter up to nearly 40 milliliters per prompt powerfully demonstrates how much everything matters. The efficiency efforts, the specific AI model being used, the underlying power generation infrastructure, the cooling systems.
Yet a single number.
It's not a single number at all. It's not one fixed problem that can be solved with one blanket solution. It's a really dynamic system with many, many different levers you can pull.
That makes it much clearer.
Hey.
But I mean, even those smaller numbers, when you're talking about billions of interactions
Yeah.
daily,
Mm-hmm.
they add up fast when you scale them globally, right?
They certainly do.
OpenAI, for example, reports something like 2.5 billion prompts per day across all its systems. That includes GPT-4o, GPT-4 Turbo, 3.5, GPT-5. While they don't give a specific breakdown for each model, when you multiply even those smaller individual query costs by billions, AI's total water use definitely adds up to something significant.
Indeed. And using those independent estimates we discussed alongside Google's official reporting, we can get a rough sense of the possible daily totals, just for context.
Okay, what might that look like?
Well, if we extrapolate based on those figures, if all those billions of prompts were like Google's reported Gemini median prompts, the total might be around 650,000 liters per day.
650,000 liters. Still a lot of water.
Yes. Now, if hypothetically all 2.5 billion daily prompts were medium GPT-4o queries at that 3.5 milliliter rate, you'd be looking at around 8.8 million liters per day.
8.8 million liters daily. Getting bigger.
And if, again, hypothetically, they were all medium GPT-5 prompts at that higher 39 milliliter rate, well, then we'd be looking at a potential 97.5 million liters per day.
Wow. Nearly 100 million liters a day in that scenario. Those are definitely big numbers, especially that high-end GPT-5 estimate.
They're not trivial amounts.
Yeah. To help put that in perspective for our listeners, maybe let's compare it to something we're all familiar with. How much water do people use for, say, watering their lawns?
That's a great comparison. In the U.S., for example, estimates suggest Americans use somewhere around 34 billion liters of water per day just for watering residential lawns and gardens.
34 billion liters
Mm.
compared to maybe 100 million for AI in a high-use scenario.
Exactly. And that comparison is where the crucial insight lies, I think. While generative AI does use water, and we're talking millions, potentially tens of millions of liters per day for popular models, its current daily totals are actually quite small compared with other common everyday uses like lawn watering or taking showers or doing laundry.
Right.
This is a really important nuance to grasp. It's not insignificant, certainly not, and it's definitely growing as AI use explodes, but it's not yet the absolute biggest water guzzler out there on the global scale.
That perspective is really key. It gives us context.
It gives us perspective and maybe also a window of opportunity to act before it becomes a much larger problem.
That makes sense. It also underscores that AI's water demand isn't some fixed, inevitable issue.
Mhm.
You mentioned Google's disclosures earlier. They really show what's possible when systems are meticulously optimized, right?
Absolutely. When companies focus on using specialized chips designed for AI efficiency, implement incredibly efficient cooling systems, and use smart software for workload management, the water footprint can be dramatically reduced.
So this isn't just a challenge, it's also a powerful opportunity for innovation and genuinely sustainable design.
It really is. And there are other effective strategies, too. Things like sophisticated water recycling systems within data centers, which can treat and reuse the same water multiple times, significantly reducing the demand on local freshwater supplies. And then there's the strategic location aspect we touched on, choosing cooler, wetter regions where outside air cooling is more feasible, further reducing reliance on those thirsty evaporative methods, or maybe locating them near abundant sources of non-potable water, like treated wastewater or seawater if the cooling tech allows.
Right, using water that isn't needed for drinking anyway.
Exactly.
And this all loops back to something we advocate for constantly on these deep dives: transparency.
Critically important here.
When companies are willing to actually release their data on these environmental impacts, especially water usage, then the public, policymakers, researchers, everyone can truly see what's achievable.
It allows for fair comparison among different providers. It fosters competition, but in a good way, competition and sustainability. And ultimately, it drives the entire industry towards more responsible practices.
So how should we summarize this whole complex picture for our listeners? What's the main takeaway?
So I think the core insight is this. AI definitely has a hidden water cost, but it's incredibly variable. It's not fixed. It's a dynamic footprint shaped by location, by timing, and most critically, by the efficiency of both the AI model itself and the infrastructure, the cooling and power that supports it.
Okay.
And understanding this variability, these different factors, allows us to move beyond just simple alarm or dismissal towards informed action and targeted solutions.
That's a really key takeaway. Understanding allows for action. And maybe a final thought for you, the listener.
Mm.
As AI becomes even more deeply integrated into our daily lives,
Yeah.
from drafting our emails to powering creative tools to maybe even helping run our homes, what responsibility do we as users have?
Do we have a responsibility in choosing which AI tools we engage with, maybe considering their potential footprint? And how might greater transparency from AI developers actually guide our collective push for more sustainable technology? Imagine just for a second how our daily digital habits might shift if we actively considered this hidden cost. Definitely something to ponder as you navigate your next digital interaction.